I, Hello, I'm Reza from Data 61. My research is mainly about signal processing and machine learning on embedded systems. And I will talk about the machine learning algorithms that we have developed to detect and identify certain behaviors of cattle using Eartag accelerometry data. The behavior classification is performed on the embedded system of the Eartag. Within the context of supply chain integrity, this work is related to the automated compliance on the farm or automated farm provenance. The behaviors that are inferred from the accelerometry data are fed to the other components of the on-farm automated compliance workflow, mainly the trust and regtech components. For example, the predicted instances of drinking behavior are used to assess compliance with certain regulatory requirements that involve the animal's access to drinking water. In this work, we have used this smart Eartag that we have developed jointly with a commercial partner. Its main components are a microcontroller with these characteristics components, an accelerometer, satellite communications, onboard memory, and solar panels. In our previous research on cattle behavior classification using accelerometry data, we have mainly utilized collar tags that are mounted on top of the animal's neck. However, in this work, we have used ear tags as we believe. From practical and commercial points of view, ear tag is a more viable solution. Although the movement patterns sensed by an ear tag do not correlate with the key behaviors of interest, as well as the movement patterns sensed by a collar tag. The accelerometer on the Eartag is a micro-electromechanical system device and has an ultra-low power operating power of maximum 14 microamps. It senses and measures the instantaneous acceleration of the Eartag on 3 orthogonal spatial axes. On each axis, it senses tiny changes in the capacitance between a fixed electrode and a proof mass that is displaced by any force applied to the supporting frame. We have run a data collection experiment in March this year for about 9 days with 7 cattle wearing our ear tags. The accelerometers were set to sense on average 62.5 values per second on each 3 spatial axes within the range of plus minus 4G. All the accelerometry data was recorded on external memory cards, and we have also recorded the footage of the area where the experiment took place using several cameras. By reviewing the recorded videos, we annotated parts of the accelerometry data with the observed behaviors. The total annotation period was around 68.6 animal hours. We then created a dataset by segmenting the labeled accelerometry data into non-overlapping 4-second or 250 value windows. Here we see 3 sample data points labeled as grazing, resting, and drinking. The goal is to develop algorithms that can predict cattle behavior from the accelerometer readings. Our behaviors of interest are grazing, resting or ruminating, and drinking. So we developed 3 separate classifiers, one for each behavior. Each classifier gets the triaxial accelerometer readings of a 4-second window and predicts the likelihood of its corresponding behavior. We take an end-to-end approach to learn our behavior classification models from the labeled accelerometry data. End-to-end learning is different from the more conventional so-called feature engineering-based approaches in the sense that it doesn't involve separate feature extraction and classification stages, but implements them jointly. We carry out the model learning or training on a suitable computing device, but aim to carry out inference using the learned models on the embedded system of the Eartag. Therefore, we have to take into account the computational memory and energy requirements, the constraints of the embedded system in our model learning. This is a sketch of our end-to-end cattle behavior classification model. The accelerometer readings are buffered to make up 4-second windows or 3 250-dimensional vectors. The vector is then aggregated to produce one set of features and go through nonlinear finite impulse response filters, then activation, then aggregation, and to produce another set of features. The calculated features are then input to a multi-layer perceptron that outputs the likelihood of the associated behavior. Both the feature extractor and the discriminator have learnable parameters that are estimated jointly during training. We have implemented the developed algorithms and the related data processing pipeline for predicting cattle behavior on the embedded system of Eartag. For this purpose, we've used the digital signal processing library of the Cortex microcontroller software interface standard, which is a vendor-independent hardware abstraction layer for microcontrollers that are based on Cortex processors like ours. Here we see the memory and computational complexity of making behavior inference for a single 4-second window. The total required running memory is less than 3 kilobytes, while our microcontroller has 256 kilobytes of RAM, plus 1 megabytes of flash memory. The inference also takes less than 12 milliseconds of CPU time, while we may need to perform behavior classification only once or twice, or once a second or a few seconds, 2 seconds, 4 seconds maybe. The CPU draws around 3.3 microamps, and even if it runs constantly, the battery in the Eartag can sustain it for around 50 hours before needing recharge by solar panels. So the classifiers don't impose any significant burden on the available resources of the Eartag's embedded system. Here we see the results of evaluating the learned models via 5-fold cross-validation over our labeled datasets. The accuracy is around 95% for grazing, 94% for resting and ruminating, 91% for drinking, with a caveat that we achieved this accuracy for drinking when we balance the dataset. And here we have the confusion matrices for 3 classifiers corresponding to 3 different behaviors. The rows show the number of data points associated with each class, and columns show the number of data points predicted to belong to each class. So the green numbers are the correct predictions, and the red ones are the incorrect ones. It's observable that the classifiers for grazing and resting ruminating have high accuracy. Drinking, not so good, because it's a rare behavior and the amount of collected data for this class is limited. That's why its classifier does not seem to perform as well when the model is applied to the whole data set. However, its accuracy is around 91% when applied to any balanced version of the data set. To assess the generalizability of the developed models to beyond the dataset from which we have learned them, we applied them to the entire accelerometer data collected during the experiment. Here we see the behavior classification results aggregated for each day during the experiment for 2 cattle. The overall ratios of the behavior seem reasonable and correspond to the relevant observations and expectations. Here, the behavior classification results for 1 cattle are aggregated over each hour of day 1 of the experiment. The Eartag was turned on around 8 a.m. This is day 2, 3, 4, 5, 6, 7, 8, 9, and the last day when the Eartag is switched off around 3 p.m. Well, to summarize, our objective that we have achieved was in situ classification of cattle behavior using Eartag triaxial accelerometry data through an end-to-end learning approach where we learn meaningful features from the data jointly with the classification models. The developed solution is fairly accurate and demands little memory and computational resources, hence can conveniently run on the Eartag. And our classifiers were to serve the requirements of the automated farm provenance within the context of supply chain integrity. That's why we consider three capital behaviors of raising, resting, and eating combined, and drinking. However, we can certainly develop classifiers for other behaviors, other animals, and other applications as well. A few other important example applications are animal health or welfare monitoring and evaluating feed intake or feed efficiency. Right, any questions?
Thanks, Reza. We don't have any questions on the chat yet. Oh, no, yes, we do. One just popped up. Do the models transfer across animals? For example, did you include data from each animal in the training set, or did you have animals in the test sets, not in the training sets?
Well, the models are learned for all animals, not individually. So they generalize to other animals. They're not specific for an individual animal.
Thanks. While I'm waiting for any other comments or questions to pop up, do you want to talk a bit more about the training on the device? Is there anything further you could add to that?
Yeah, well, yeah, definitely that's an important next step for us, and we definitely want to achieve that as well. We are working on that. It has its own challenges, obviously, because training requires much more computational power and memory, working memory. But that's something we're definitely working on that, and it's a lofty goal. Basically, it's not as straightforward. Another challenge with that is to transfer these labels, annotations to the tag while it is learning. It's another challenge that we have to solve before attaining any learning training on the device.
Thanks, Reza. I don't know if you can see the questions, you probably can't, but Phil's asked, would it matter which ear the tag is in?
No, it doesn't matter, I guess, but it should be consistent, I guess. If we learn models learned from data collected on left ear, they will work on the tags installed on the left ear, I guess. We haven't tried whether it will work on the other one. Can't say anything about it.
Okay, thanks. I'll ask another question while we're waiting for anyone else to post questions. We've still got a few minutes to go. Hold on. Here's another question from Aaron. How do we balance the data sets for the rare behaviours? How do we get more records of these rare behaviour events?
Well, there are several ways of doing this in the world of machine learning. We can oversample the rare class, we can downsample the dominant majority class, or we can make synthetic data points to increase the number of data points for the rare class. What I've done so far is just downsampling, which seems to work well and is the least complicated solution so far.
Thanks. I'll go to my question unless something else pops up. And that's about if you want to talk a bit more about how your end-to-end performance compares with that of the feature engineering-based ones.
Right. Yeah, that's quite interesting, actually, because I originally started with looking into, I guess we don't need the same. I started with looking into these conventional feature engineering-based solutions originally. But they didn't perform well. So it's not just a more advanced solution using the choice of end-to-end learning. It's not just, it is more like cool or fashionable. But that actually is the only solution that works and delivers the performance we want. The feature engineering-based solutions are very ad hoc, and they're very difficult really to get to work, and they didn't work to the accuracy that we wanted so far in this project. So I use end-to-end learning.
I've got another couple of questions now. Now they're coming in. How far do you see this going? Do you see further build out of the tags to include chemical detections such as methane emissions and the like?
Yeah, definitely possible if we have the right sensors and collect the data that we want, and we can definitely analyze the data and build relevant models and see what can be done with those sensor data. We have now the means to learn models that will run on the Eartag, so we can definitely consider any sort of sensor data in any application.
So Phil's sort of, I guess, related question is, how hard or easy is it though to integrate those different sensors sampling at different rates? Is that a challenge?
Definitely, it's a challenge, but before doing it, I can't really say anything for now. But it's doable. That's what I think. And the way we are doing this now, our processing model building, I'm very positive that we can do a lot with this. And you see, even these sophisticated classifiers are taking only 1% of the memory or requiring like 12 milliseconds to run. So there's plenty of things we can do on these tiny devices.
Great, thank you. I think we've just about, we've reached the end of the time for this talk. So thank you, Reza, very much. Or maybe one last very quick question. Do these tags link into NLIS?
Yes, that's one of their main functionalities anyway.
Great.
That's not my expertise, that's not my work, but
sure.
Maybe Aaron and Greg can comment on that.